Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello, welcome to Physics with Beth and Beth. I'm Beth. We're in AP Physics 1, that Unit 5, which is Rotational Dynamics. And today we're going to be talking about that pulley with mass. All right, in the first, if you're doing this as a year course, in that first semester, we talked about the force dynamics unit, Newton's second law, and we did pulleys that had no mass. When we had pulleys that had no mass, we said tension 1 equals tension 2. All right, in other words, let me draw this out. If I had an outwood machine and I have a block 1 and I have another block 2 and I tell you it's going this way, and we said, hey, T1 equals T2 when the pulley has no mass. And I always told my students, just trust me until we get to the next semester and I'll prove that to you. All right, well today's the day I'm proving it to you. Okay, now also you would have that force due to gravity would have been larger than that T2 because unbalanced forces moving this way, so it could have been like this. And then this one would have had to be smaller than T1 because again, unbalanced forces, this one's moving up, this one's moving down. So that's kind of what that free body diagram would have looked like, but T1 would have been the same length as T2 in magnitude. Okay, I'm gonna go ahead and erase this and then we're gonna get started on our real problem, which is now when you introduce mass. So what happens when you introduce mass to this pulley? All right, here's what's happening. Now you have a rotational inertia. This pulley is going to rotate, is going to resist rotation. So it's going to have rotational inertia, that I value, or what we also like to call moment of inertia. They mean the same thing. It also means that there's going to be forces on it that are causing it to rotate, which means we have torque now. So if this pulley has mass, we now have torque introduced, and we have some moment of inertia or rotational inertia introduced. Now the first thing we're going to do is a free body diagram. There's actually 3 free body diagrams here that I'm going to do. The first one's going to be the pulley. I have this pulling down here. I have this tension here. I have another tension here pulling down on the pulley in both directions. Those are actually perpendicular forces, right? And really, we always just show this hanging in midair, but really it's hanging on a string from a ceiling. So we have another force here, and then we have the pulley actually has mass now. So it has force due to gravity, and I'm going to pull that out of the pulley. This is going to be tension, I'm going to call that tension 3. I'm going to have to call this tension 1 and tension 2. All right, so, but here's the deal. 2 of those forces go through the axis of rotation. Remember, torque is R times that perpendicular force. R would be 0 because R is the distance from axis of rotation to where the force is applied. For T3 and that force due to gravity of the pulley, it's just 0. They produce no torque. This one produces no torque. It's a force, just doesn't produce torque. This one doesn't produce torque. But T1 and T2 do produce torque. All right, so that's important to know. Now that's my free body diagram for my pulley. Now I'm going to do my free body diagram for block 1 and block 2. By the way, I probably should have told you the problem. Mass 1 is 1 kilogram, mass 2 is 2 kilograms. The mass of the pulley is 0.50 kilograms, and the radius of the pulley is 0.25 meters. They might have said 25 centimeters, so don't forget, if it's in centimeters, get it to meters. They want to know the acceleration of this pulley. They want to know T1 and T2, because once that pulley has mass, T1 no longer equals T2. All right, now let's go ahead and get started. I'm doing a free body diagram for mass 1. Mass 1 is less than mass 2, which means that this whole system, once it's let go, is rotating clockwise here. I'm going to call that direction, typically we call clockwise negative, counterclockwise positive. But when you're doing systems, I'm going to go ahead and call that positive the direction of acceleration. I do that on ramps. I do that on systems of blocks if you've got them side by side and they're pushing in one direction, or on any of these pulley systems. Direction it's moving I call positive, and that keeps your acceleration positive. Okay, mass 1 is less, so it's going to have a little force due to gravity 1, and it's going to have a tension that is bigger then the force due to gravity, because it has to be unbalanced for it to be moving up, because on this side, of course, it's moving up, right? It's going this way, and then it comes down on this side. Then that's going to be T1. Then T2, we're going to find is larger, and I will explain that momentarily. So I'm going to make this longer than T1, because to represent its magnitude is bigger. And then my force due to gravity too has to be longer than this tension, or it wouldn't go down, because this block is moving down while this block is moving out. So I have unbalanced forces here moving down, which is our positive direction. And I have unbalanced forces here moving up, which again is our positive direction, this whole clockwise, okay? All right, hopefully you understand that. Now let's get to the real problem. We just said this pulley has rotational inertia and it has torque. When you have a pulley with mass, I would always start with Newton's second law for rotational motion. Just like in the example I drew over here where the pulley had no mass, we always started with Newton's second law for linear motion. All right, but once that pulley has mass, we've got torque, so we are going to Newton's second law still, but rotational motion. The sum of the torques equals moment of inertia times the angular acceleration. All right, now we're gonna remember that this pulley is a disc, and so that I is gonna be 1/2 mr squared because it is a disc. Perfect. All right, I'm gonna sum up my torques. I have 4 forces here. We've already said these two do not produce torque, it's 0. So I have a torque from this tension 1, and I have a torque from this tension, this force or tension 2 that is producing torque. So I have 2 torques here, and remember my positive direction is this way. So I have a negative torque from that tension 1, and if you like to put it like this, you can do the force and tension. I usually just use a T, but you can do a capital F with the capital T as a subscript. All right, and then this force, this tension 2 is pulling in the direction of acceleration. So I'm going to call that positive. So I have a positive torque for that tension 2 force. That's going to equal my moment of inertia, or my rotational inertia of the pulley, which is 1/2 mr squared. Now you need to be very careful on subscripts here, because you're going to have mass of the pulley. You've got mass 2 and mass 1 of the 2 blocks. So I'm going to keep that P in there for the pulley. Now I have angular acceleration. Okay, they have asked for a term for linear acceleration. Remember, this one is rotating in angular, but that angular rotation, that angular acceleration is related to the linear acceleration that this one's moving up and this one's moving down. All right, so it's related. That angular acceleration is related to your linear acceleration. These are at rest and then they start moving. They have linear acceleration, change in velocity over time. All right, we know that acceleration, linear, is r, the radius, times your angular acceleration. All right, I'm going to divide both sides by r, and oh look, I have an expression now to put in for this angular acceleration in terms of linear, which is what they've asked for. So that's a good start. We're getting there, so I'm going to put that in. All right, now we're going to look at this problem and see what to do. My torque, remember I wrote that over here, that torque is equal to R times that perpendicular force, and these are in fact perpendicular forces. So that's going to be a negative R times that tension, I'll go ahead and put force, of tension 1, plus R, again, they're both at the edge of this disc, so they're both a distance R from the axis of rotation of where they're applied, of force tension 2. And that's going to equal 1/2 mass of the pulley, and one of these R's cancel, so I have R times my acceleration. Okay, it's looking good. Now I look and go, oh wait, everybody brought R to the party. Yay, cute party in the USA, get up, do your dance while you're marking out your R's. And we have a negative force of tension 1 plus a force of tension 2 equals 1/2 the mass of the pulley times acceleration. Okay, now we don't know our forces here. And if they were asking for an expression and not an actual number, it wasn't a mathematical, it was like a qualitative problem, they're not going to allow you to have tension force at 1 and tension force 2 in here at all. So we need to come up with an expression of what we know so that we can answer this. Because if we're looking for a number for acceleration, we know mass of the pulley, but we do not know these forces of tension 1 and tension 2 yet. So this is where this problem becomes a little bit more complicated. Maybe not complicated because you've done this first semester, but more steps. So we're going to go ahead and I'm going to put a little line here and a little line here so we can keep this separate. All right, and I'm going to do the sum. I'm going to do block 1 first. The sum of the forces on block 1 equal mass times acceleration. And that's going to be mass of 1. I'm only looking at one block. Here I was looking at the whole system on that pulley. Here I'm just looking at block 1. So I go to block 1 and I know this direction up, and on this side up is positive because it's moving clockwise. So tension is positive, so that's going to be T1 minus force due to gravity 1, and let me go ahead and keep consistent with my force of T1, minus my force due to gravity equals mass 1 times the acceleration. All right, I'm just looking for, you're like, what are we doing? Why are we doing this? Because I need an expression to put in right here so I can find my force with what I've been given, which is just the masses and the radius. Okay, that's what I'm doing. So I have my force and my tension 1. I'm going to solve for it because that's what I'm trying to find an expression for. I have M1A plus force due to gravity we know is M1G. This is going to be M2G. So I'm putting in M1G. Okay, I have an expression now that I can put in here, but don't forget this negative. It's got to be distributed. So I have M1A plus M1G. We're going to do the exact same thing for tension force 2. So I'm going to kind of cut this in half and I'm going to say, okay, now I'm dealing with block 2. I'm going to do my sum of my forces on that block 2 equal mass 2 times acceleration. So again, system first, and now we're going to go do our individual blocks. I look at my free body diagram for my for my block 2. I have tension up. Okay, tension was up here too, but it was in the direction of acceleration. This is opposite the direction of acceleration. So T2, let me keep constant. Sorry, I keep forgetting that. Force T2, I usually just use a T. That's minus, because that's opposite the direction of movement. We said direction of movement's positive. And then we have force due to gravity of 2, which is in the direction of motion. So that's going to be force due to gravity of 2. And that's going to equal mass 2 times your acceleration. These accelerations are all the same because everything's moving at the same linear acceleration. And again, one more time, just to make sure you understand that. The direction of movement on that block 1 was up, so tension 1 was in the direction, so it was positive. Force due to gravity was in the opposite direction, so it's negative. Okay. All right, now I'm going to solve for this because again, now I want an expression to put in here. All right, so I'm just going to add that whole thing over because I don't like dealing with negatives. So I have M2 mass 2 times acceleration plus that force of tension 2. I'm going to subtract this little expression from both sides, mass 2 times acceleration. And for force due to gravity of 2, we said, hey, that's M2G. So M2G minus M2 times acceleration equals that tension force 2. I'm going to take this little expression, plug it in for here. So I have M2G minus mass 2 times acceleration. So mass 2 times little g minus mass 2 times acceleration equals 1/2 mass of the pulley times acceleration. Okay, we now have an expression, but what we really need is an expression for acceleration, and then we'll plug in our numbers. Now, a lot of people are tempted to just mark out masses. Look, everybody has mass in their expression. No. Mass 1, mass 2, and mass of the pulley. So they are not, you cannot mark those out. All right, I'm going to go ahead and distribute this. I have M1 times my acceleration plus a negative M1 mass 1 times little g. All I did was distribute this negative because we recognized that was negative torque that tension force produced. All right, I still have mass 2 times g minus mass 2 times acceleration equals 1/2 mass p times acceleration. Now, and that's mass of the pulley times acceleration. All right, now I'm going to get all of my accelerations together on one side. All right, so I have negative mass 1 times g plus mass 2 times little g. That's going to equal 1/2 mass of the pulley times acceleration. I'm going to add this little phrase over plus mass 2 times acceleration, not a phrase but an expression. I'm going to add this little expression over plus mass 1 times acceleration. Now I'm going to factor acceleration out. This problem just keeps going. It's the problem that just keeps going and keeps giving. It's like the Energizer Bunny. All right, plus symbol 1. All right, on this side I have a negative mass 1 g plus a mass 2 little g. All right, now I'm going to divide both sides by this lovely expression of half of the mass of the pulley plus the mass 2 and mass 1. And I get finally an expression for acceleration. 1/2 mass of the pulley plus mass 1 plus mass 2 equals acceleration. I now have an expression if that's all they asked. However, I wanted an actual number. So now I'm going to put in for mass 1 is 1. Little g, you can use 10 for your exam, and NAP, I like to use 9.81, so my number may look a little different than yours if you're using 10, but not much. It shouldn't be much off. Mass 2 is 2 kilograms. Little g is 9.81. Mass of the pulley, it's going to be 1/2 times 0.5. And then mass 1 is 1 and mass 2 is 2. So I'm going to go ahead and write that in just so you can see what I did. 9.81 plus 2 times 9.81 over 1/2 times 0.5 plus 1 plus 2. That acceleration is going to come out to be 3.02 meters per second squared. And that is your acceleration. All right, that was the first question. The second question was to find T1 and T2. Okay, you just plug it in here. That's all you're doing. So if I want my tension force 1, it's going to be 1 times that acceleration I just found, 3.02, plus 1 times 9.81. And you would get a tension force of 12.8 newtons. I'm going to do the same thing for this tension force 2. My mass 2 was 2, little g is 9.81, mass 2 is 2, acceleration is 3.02. That equals that tension force 2, and that's going to be 13.6 newtons equals tension 2. Look, they do not equal each other. We said they would not equal each other, and they do not. And here's why tension 2 is bigger. I told you, I'm drawing it bigger. I'll explain it in a minute. The tension in this line, wire, cable, whatever it is not only lifting block 1 like it did in first semester. If it was only lifting block 1, they're equal. But it's also rotating the pulley. And the pulley has rotational inertia, meaning I don't really want to rotate yet. And it's being a little stubborn, and so it takes some force to get it to rotate. So this tension is moving the pulley plus lifting this block. So that's why T2 here is greater, and I can use the force with T, is greater than 1. The tension here in this block is just lifting the block. This one's lifting the block and moving the pulley. Okay? If that helps kind of explain that. So if it was going in the other direction, then T1 would be greater, because T1, if it was moving this way, then T1 would be, if we had our blocks here, then T1 would actually be moving the pulley and this block. So then in that instance, if it's moving the other direction, T1 would be greater if this was T1 and this is T2. Now, something very important to note that I should have stopped right here and shown you. Look at this. We have tension force 1. We have tension, the tension force 2. This one's negative, this one's positive. If the mass of the pulley is 0, look what happens to this whole side. Here, I'll use this one. Look what happens. If the mass of the pulley were 0, this whole side is 0. And then add that over, and look, tension 1 equals tension 2 if you had no mass on your pulley. But we have mass, so that's why this was not that. It was 1/2 mass of the pulley times acceleration, because our pulley had mass in it. Okay, that's the problem. Thank you for watching. If you like it, please give us a thumbs up. Subscribe if you hadn't, we would love that. And pass on to your friends if they're struggling in physics and you think these videos help. But thank you so much for watching, and happy physicsing.